Hello, is there anyone here? Good, seem to have a connection here. This is just really an update on how this peculiar research program is going, and there are quite a few ideas which I'm trying to find the correct order to kind of present them in, but the idea is to look at the twin vector state formalism applied to QFT. And so the idea is this, that if we take classical mechanics, let's see whether this pen is working. Classical mechanics, oh, that's got a bit strange. Whoops. Classical. Oops. That's initial conditions. That gives us a uniquely defined dynamical system. Now, for quantum, we have initial conditions plus final conditions plus unitarity gives us a unique quantum system. Now the idea is, what is this quantum system? It's a uniquely defined system. So this is deterministic. So let's see where this takes us. We can imagine that we've got a quantum initial condition and that's evolving, say, into multiple states like this. Then if we pick one, we get a unique history if we go backwards in time. Now, so the idea is if we look at this, why is this thing going so crazy? That's our S matrix for a quantum theory, where we normally think of phi A as being the ingoing particles, phi B being the outgoing particles, S being a unitary S matrix operator, and this giving us the amplitude of this interaction. So with the phi A incoming and phi B outgoing. Now we just take this as just look at this as a time reversed system, where we could equivalently think about this as an interaction between phi A initial conditions traveling, well, let's take phi B here, traveling forwards in time, and then phi A traveling backwards in time. So we have initial conditions here, one moving forwards in time like that, and one moving backwards in time like that. So I'll just try and get this button that's so annoying. Okay, so, and then we have some kind of interaction which is, as we can see, is multiplicative. So this modifies, if we just take this time reversal view, we start with, now let's look at a peculiar case of what these initial conditions and final conditions going to mean, because uh, if we start with a point in space-time and we just split the vacuum here with an operator, then we're going to get a shock wave traveling forwards in time, and we're going to get a shock wave traveling backwards in time with negative energy. So we can see that the total energy is 0 here. And what we're doing is we're putting the positive and negative modes of the field, so that these are essentially ghost modes of the field because they've got negative energy. But so what we do is we essentially double up the number of oscillators that we're coupling in the quantum field theory. So we can imagine we've got our forward moving oscillators, which make a set like that. You know, so we've got all our coupled oscillators and they're all moving forwards in time like that. And then we've got a bunch of negative oscillators, which are all moving backwards in time. So relative, these have negative energy and these have positive energy. But this is all relative, because relative to this, if you're in this space, this thing has negative energy. So what we're doing is we're taking the potential negative modes of the quantum field and putting it into a separate interaction field. So we're actually imagining these phi A and phi B now being in completely different sectors, and they're interacting, these sectors are interacting via this S matrix like this. So normally, you see, we imagine the flow of an S matrix going like this, so getting some kind of interaction node here and then something popping out like that. But here we're regarding it as two modes. It's the same picture, but instead of just getting an arrow of time moving upwards like that, we've got two arrows of time, both of which are wave-like, and it's only their interaction that creates a physical universe. So here what we do is we imagine the forward modes going like that, and then we have our negative modes going like that. And they're interacting all the way along. Now, what is this looking like? What this does is it's covariant with regards to preparation and measurement. So that's one of the most important things. So imagine now we have a vertex here. If we've got no interactions, no self-interactions, then this wave is going to just carry on off to infinity without ever being observed. And likewise, the negative mode there. Now, the interesting thing is what happens if we put this on a compact time? Then, by having our circular time here, we put one mode there, one vacuum splitting operator there, we get a forwards mode and a backwards mode, but they do interact, and they can interact like this to create a function that it locally, so what this looks like is if we imagine things traveling at the speed of light, then we get that diagram, like this, where we have, just the far fields are being cancelled off. So this is essentially putting real physical meaning to Feynman diagrams. Normally they're just regarded as computational tools, but here they're quite essential, because in order to actually, so when we're operating on a compact time like this, we land up with these this is a single operator now, and it's creating the forwards modes like that and the backwards modes like that. But so this is, so here we have a propagator, um, which is essentially something like um, H here, and then we have its the propagator for the other side is just something like H on that side. So now we can see we get the S matrix out of this. We've got the same, this is an automorphic form because we've got essentially a creation and annihilation of the same particle. But the thing to realize is this is not strictly a causal theory because of the fact that we do actually have in quantum field theory superluminal paths. But what happens is that instead of these paths in the normal picture, the problem is that the measurement takes this whole far field and collapses it onto a point, and that's not friendly with regards to covariance. But here, because the actual collapse starts midway through the path of the particle, so this midline is absolutely key, and it kind of corresponds to the line sigma equals half on the zeta function. We can clearly see this has, is an automorphic, but there is automorphic functions going on here. Now, so what happens is this means that we've actually got a formulation now for taking a Lagrangian and just simply adding in these backwards modes, but we are essentially forced to decompose the Lagrangian into these local interaction terms. We actually don't seem to have much of a choice in doing that, because what we're doing is we're taking a path from A, and then we need to know where we need this image of where it's going to be measured, and then we can produce this field which has this symmetry between them. But unlike the previous drawings, this is a genuine field that is stretching off and filling over into the whole of space-time, past and future. So this is a extraordinarily non-local theory, but what's happening is it's localizing at interaction points, and we can compute it using Lagrangians. But what we need to know is we've got the propagator here, that it requires the final conditions post-selection. So what that means, now what's really, let's save this as something, QFT1. Create a new one. So now, what we see is we actually have for any interaction. All right, so first of all, we have our propagators like this, and so let's say we have an interaction between these 2 points. So there's and then we have our midpoint here. First of all, this has to be in a region, the not propagator gives us the probability of going from there to there. And so what we're saying post-selection is assume we've gone there to there. Now we can create this, we can take the Lagrangian field and run it backwards, and that generates this new field which represents the flow of quantum information between these two interactions, where we also have long tails on these two. So this is some kind, we've got some zeta function like behavior going on here, the xi function, where we have this line, we have a line of symmetry, but this is now stretching all the way off to infinity. But most of the area, most of the probability lies in this causal diamond. But this is only probabilistic. There is this tail outside, and it's only in the limit over a huge number of, infinite number of observations that you'll end up with the delta function. So the speed of light is an average property, rather like it is in QED. Well, it is, and in fact, what we're looking at here, let's assume that we're looking at a kind of QED. We're starting with QED because it's the simplest of the gauge theories. So, but what we notice, all right, so what we've done is we've got our very, and you can see here immediately that here we've got the vacuum energy. We're essentially borrowing energy from the vacuum. All right, so let's look at this point. This is really, really key. So the interaction points. These, what are these? Is it a compact region, or is it an actual point? Now, if it's a point, then it's a Dirac delta function, and then that means that it corresponds to a frequency f, which is the momentum. So if that's the position, then the momentum is entirely given by it's just a single frequency. And so that means that we've got this wave spreading out in quite a simple way, but with really very little damping going on with regards to the high momentum part of it. It's really UV, the UV side of the momentum is really, really high. It's got this very high UV. But what this seems to do is not regulate it, but localize it, kind of semi-localize it. So instead of it just collapsing from this absolute mess. So what's going on here, right? So we've got a part, we can imagine this in terms of path integrals, that we've got a path and it's taking every possible path. And none of them are particularly more or less likely than any others, other than it just having the momentum of a sine wave. So that's just going off to infinity, and that's just going off to infinity the other end. And so we've got this really, really intense quantum field being generated, but luckily we can collapse it here rather than collapsing it here, and from here the view is exactly the same, but we've just got, you know, a reflection over the line of symmetry. And so this, what happens is we take our, so we decompose our quantum field Lagrangian into some kind of Feynman diagram, it might be really, really complicated, but what we want is to essentially pick this at random so that we have some, we imagine that we have every possible state of every possible Feynman diagram, and we have some measure on this space, and then we pick one of them. Well, but basically it doesn't matter, because what happens is once we pick the final state, the space actually decomposes into interactions because the field becomes uniquely defined. So really what happens is it becomes a case of analysing these interaction localities quite carefully, because we don't need to assume that we're breaking it down into Feynman diagrams. It's only one of the possible ways of evaluating it, but in this particular case I haven't seen any other easy ways to do it, so let's just stick to this because we know it works to some extent. So what we're doing is we're essentially, all right, let's yeah, this isn't quite right because we want some symmetry in it, but let's assume we've got some complicated Feynman diagram like this. Then we just basically start thickening it out, and so each of these has, instead of just a propagator field, it has a genuine and here remember we're not, it's not, we're just drawing where the bulk of the wave function is localized. It's not actually all in here. It does spread out over all of space and time. And the other thing to note about this is the entanglement of it all. That basically interactions are telling us entanglement, because these outgoing particles here are entangled, but if we reverse it in time, then we can regard it as these outgoing particles are entangled. So incoming and outgoing particles are entangled in this system, which is, I guess, a side effect of the superdeterminism of the system. But that's not to say that the system is computable, easily computable, but it is in a certain sense deterministic, because we've taken the wave equation and then by looking at all the final conditions, we've essentially foliated the space. We've decomposed the multiverse into independent threads. Now, this might not be correct. It might be, for example, that the threads do in some sense interact, and that might well be the case. But I think it's best in this situation that, like any, just to look at the simplest case first, because it's just more complicated to assume that we've got interactions between the threads. But that does seem very plausible, and there do seem to be approaches to do that, which maybe I'll talk about later. But let's for the moment assume that we have non-interactions between the various threads, so that the process is at this level unitary. Yeah, but that, as I said, that might not be the case, and things like black holes, event horizons, and Unruh radiation do suggest that a dynamic model is more appropriate. But so let's look at this system and let's see where it kind of breaks down, because it's bound to, it will and does break down. So let's see how it does. But for the moment, we'll investigate a few more of the consequences of what seems to be a very, very minor modification, because it doesn't really change any of the probabilities at all. And that's one of the benefits of this, because there's a huge amount of work that we have to agree with, and so any changes have to be extremely small, because QED works to such high precision that we can't change many things about it. And so here, instead of by post selecting, by adding that tiny little thing to collapse the system into some kind of, and it's not really a what would be, I call a quantum state or a classical state, somewhere in between. It's not really even a stringy state. What we can say is it's got endpoints, two endpoints, and a quantum field associated with it. So we could regard this as a kind of stringy-like object, where we have our points A and B, and then we have all possible paths like this. And so that essentially corresponds to all the different string modes that we could have linking those 2 points. And we can see that when we do the amplitudes, we do actually, with this time reversal, with these, once we have this symmetry, field symmetry, in fact the path, this isn't obvious from here that it's putting additional constraints on any paths that we have to take. They have to essentially be symmetric about this axis, otherwise we're not going to get, but that's like the only restriction, it seems. So yeah, we do get a slight restrictions on the space of paths, which is no bad thing. And which shows immediately why this one is wrong, because the paths all have to obey this symmetry. So they all have to obey the time reversal symmetry. So they have to like reflect around here, like that. So they're all even functions. And what's interesting is if we look at this is essentially a singularity, if we like. And so what we would really like is for these, alright, so let's assume it's not a singularity, that it's got some compact size that's not, a compact volume. Then first of all, if it's compact, it's still got an unbounded Fourier transform in momentum. So it's still going to fill up the whole of space. And but there is one possibility which Gerard Terhooft has investigated, which is if this is if we use a finite Fourier transform, so over a finite field, or just any finite Fourier transform, and then we can have a position which represents a single frequency, and that will correspond to a sine wave in momentum space. But the thing is that in this case it stops, so there's a maximum frequency that can be reached, and so that would mean that in this case there would be a maximum speed of causality that could never be exceeded. It's not the speed of light. I mean, well, it could be, but I think experiments show that it's not, but that obviously has to be checked. But yeah, I think the far field has been investigated pretty well, and it's not non-zero. So, and yeah, in interference experiments, the far field computations are important. We can't just chop them off. So, what does this mean? It means we've got two very, very different models. Oh, but on the plus side of this does mean that we're dealing with a finite dimensional Hilbert space. And gravitationally, so this has plus points of using the finite Fourier transform, and that's its finite dimensional. And and that does ring true for gravitational theories. So, but essentially, for the moment, we can ignore it because we just are assuming that we got some Fourier transform over some field. So, but we won't necessarily assume whether it's a real field or something stranger. Either possibility is plausible, but and there are all kinds of weird ways that we could, you know, extend the momentum off if we wanted to, because this is periodic. So there's all sorts of tricks that could be done. Who knows? It could be that we have a finite dimensional generator, and then that generator generates the far field. It could be this far field. This does represent a maximum interaction speed for entanglement or something, but that does seem strange. But because, well, hey, let's wonder about that later. So, but what we have got now is this idea where we go from a Lagrangian density to an automorphic path integral, which then yields us this S matrix covariant interaction. So this is the twin vector state formalism, which actually dates back a long time. 1921, references going back to 1921. So it's not a new idea, but and a lot of these ideas are not new. It's just how to kind of link up what is known in some kind of way that makes consistent sense. And that's all I'm really trying to do here, because, you know, but fundamentally, when you get down to it, quantum field theory doesn't seem to be that difficult, because at its conception, it's just a bunch of coupled oscillators, and the coupling, you know, we can vary the metric, and so the closer that they get, the more coupled they're going to be, and the further that they get, the less coupled they're going to be. And then the propagator tells you the probability of a quantum wave traveling from one to another. And then, but what we've got is now the propagator doesn't just give you that, it actually gives you this quantum density, which is a field in its own right. And so the thing here as well is that it's a field in its own right now. Not the wave function, but this one, A B, is a genuine. So the interaction between A and B. This is a field now, and it is the basic density of energy that we're going to use for relativity. And now it gets really, really strange, because if we put these, right, now let's assume these are singularities. But we vary slightly only slightly from Tsvf's setup, but it's almost identical. In Tsvf's setup, he has a singularity and a black hole event horizon like that, and he is identifying antipodes. So essentially he lands up with a hemisphere which looks a bit like an Einstein-Rosen bridge once he identifies the event horizon, with its opposite side, and then you get this picture, but where you have this critical projective twist, and that twist means that you cut out or only odd modes survive. Exist on the event horizon. And so we're decomposing this into spherical harmonics on here, rather than just the Fourier, the normal Fourier mode in a flat space. We get the decomposition into the spherical harmonics. Now, what we're doing is, now the important thing here is, so this is a projective hemisphere, and we're essentially identifying opposite sides of this black hole. So it's not really a sphere anymore. It's this peculiar structure. But in this theory, it is still a sphere. What we've got is a sphere here, and a sphere here, and then a kind of, if you like, they both got a singularity in the middle, but for the sake of drawing them, we'll put the singularity in the middle there, and then we have a kind of cross-cap structure. So, but it is implementing exactly the same as 't Hooft's antipodal transform, but it's mapping, say, that one to that one. So what that means is that that one, this point here, instead of mapping to that point there, goes through and through to that point there. So we're still got, that would correspond to that point antipodally on 't Hooft's map, but we lift that to another sector, but on the other side there. And this gives us, we've also got another degree of freedom here, because we put this twist in, but we can also put some arbitrary gauge transform in there too. And that's going to be quite useful, as we're going to see, because I think that's key to actually how to construct a universe that survives, an eternal universe. Without that, we can only seem to make virtual particles. Now, so what have we got? We've seen that the inner product, once renormal. Of course, I'm assuming here that we're renormalizing everything so that this is a unitary field. And we can imagine, say, this is an electron moving that way. This is a positron moving that way, but that's essentially the same as an electron moving that way, and so the whole while this object remains electron-like, with an electron-like flow. But here we can imagine that the space is expanding after preparation, and then after the mid-path it starts contracting down to its measurement point. And now this is really where the fun starts, because it's like, let's start to analyze some systems using this. So let's just save this. As QFT2. Select everything and cut. Okay, so now let's imagine the classic experiment, which is really one of the founding experiments of quantum mechanics, which is the twin slit experiment, because this will demonstrate some interesting properties about this particular, the twin vector state formalism. what we imagine is that we've got a source here, and now we know from quantum mechanics that we can model this as wave functions spreading from here, and we know the probability of all of this. We just add everything up, we get an interference pattern which may or may not have a spike in the middle, depending on whether these the phase of the relative phase, so of these two gaps. So, but let's assume just for that there's a non-zero probability of it landing up in this region, and that we actually get a measurement here. So now what we do is we just basically draw the picture as we did before. So we join we take a midline like that, and we take the mid path between them. And then we can just take the propagators. So the propagators are going to go out as we've seen like this, but then they're going to also go out like this in reverse time. And this is again just showing the causal like patch of the diagram, but it does extend, and so but we've got to obviously do it just for the moment way outside there, and we imagine that this is a pure absorber, which of course doesn't exist, but just for the sake of the experiment, of the thought experiment. But now we can see that we get this really rather interesting looking density where there's like most of the probability is going to be in this region here. And now what we see is this is really a very faithful representation of Heisenberg's notion of quantum mechanics, because what we're doing is we're saying this thing is a real thing between here and here. It's a point-like particle. But between here and maximized here, this thing is wave-like. So it's going particle, wave, particle. So we can't say this thing is a particle or a wave. It is technically both, and it depends on what part of the cycle you're looking at to decide whether and what it is. And so in this case we find, yeah, the probability is going to be in this rather interestingly shaped causal patch, and most of the, but there is always a probability of it, yeah,